Angela Bragaglia and Eugenio Careta from the Bologna Observatory. And we will hear the presentation about investigations of the globular cluster, interesting globular cluster. So please start, Angela.
Thank you, Grazina. Thank you, everyone, for joining us today. And that was observed by flames at the VLT. So among the Milky Way globular clusters, the most massive ones are particularly interesting because they could represent the nuclear clusters of ancient dwarf galaxies, now merged into the Milky Way. And also they are interesting because some of them are expected to show a significant spread in metallicity, and this is an important information to understand how they formed. So we concentrate here on the massive, old, and metal-rich globular cluster NGC 6388, which is presently located in the bulge of our galaxy. And we wanted to investigate it. So we obtained high-resolution spectra of stars in these clusters, and we used flames at the VLT and obtained spectra for 181 giant stars in the cluster. And based on our analysis, the cluster does not show any significant metallicity dispersion, and it shows instead the normal anti-correlations between light elements typical of the globular clusters, indicating the presence of two stellar populations or stellar generations. And finally, NGC 6388 seems to be a genuine bulge cluster formed in situ and not accreted from outside. So, having already presented the conclusions, let's see how we got there. So, to make a long story short, essentially all Milky Way globular clusters display a distinctive signature in chemistry, large uncorrelated variations stars to oxygen and sodium and to other elements. So this has implication, this distribution and star-to-star variation has implication on how the cluster formed, as these abundances cannot be produced by the stars that we are seeing today. They must have been imprinted by more massive stars of a first generation, of a previous generation. So the first result and the first robust demonstration that this kind of distribution in light elements were not an evolutive phenomenon, but it was intrinsic to the cluster formation, was obtained using UVs at the VLT in the early 2000s. So what we see here is part of our work on anti-correlation in globular clusters, done using flames at VLT. We obtained for each cluster an average of 100 stars. And with this number of stars, it was possible to not only to see that each cluster presented an anti-correlation between sodium and oxygen, but also that they differ in size and differ in extension. And based on the chemical abundances, it is possible to separate stars in a globular cluster on a primordial component which has the same composition in elements of field stars of the same metallicity, and in stars which belong to a second generation that we indicate here with I and E, meaning P stands for primordial, first generation, I and E are second generation stars of intermediate and extremely modified composition from the original one. However, even if we got an average of 100 stars per cluster, in the case of 6388, which is a very massive cluster, we had only 32 stars in 2007 when these data were collected. And this was due to the fact that we are talking of a bulge cluster and there is a large field contamination. So we observed more than 100 stars also in that cluster, but most of them were not members of the cluster. So the field contamination was very difficult to keep under control in these conditions before Gaia. So to get a large sample of stars in this cluster, we then used a simple approach. We went to the ISO archive and pre-selected because for this cluster there were already observations beside our original ones, and downloaded all the spectra and pre-selected stars to be observed again or based on the radial velocities, because of course some of those stars were in the archive but had not been observed with the right setup to derive oxygen and sodium. For instance, the largest sample we could study was already published by Lantoni collaborators, but it only used HR21, which does not contain lines of sodium of oxygen. So by doing so, we were able to move from 32 stars in our original papers to more than 180. So by adding new observation to stars already in the ISO archive. Of these 185 stars, 150 were observed with the giraffe setup, which is a medium resolution spectra, about 20,000, and 35 were observed with UVs at very high resolution. This combination permits a much better definition of the chemical properties of 6388. And we see here the sodium-oxygen anticorrelation. And we see that stars may reach even very large sodium overabundances. And the colors here indicate the different populations. So blue stands for primordial, red for intermediate, and light blue for extreme stars. So red and light blue are second generation stars. And in this case, with this large sample, we were also able to see if there are differences between the extension of the anticorrelation for red giant stars, asymptotic giant branch stars, and red HB stars, because we observed small numbers also of these two. And yes, there are some differences between those. We have first and second generation stars in all samples, but the most extreme variations in oxygen and sodium are all seen in RGB stars. And contrary to the large variation we see in light elements, we do not find any spread in the iron abundance in this cluster. And the small dispersion we see here, and we are the last line in red, it's perfectly compatible with the measurement errors. And I want to underline this because there has been a claim that the cluster showed an intrinsic metallicity spread based on MUSE data of many more stars than we have. However, the MUSE data have a much smaller resolution, so their metallicities are intrinsically less precise than the one we can derive from the high resolution spectra we have at hand. Also, a spread in metallicity could have been expected based on the chromosome map of 6388. The chromosome map, it's a combination of magnitudes in different filters from the space UV to I magnitudes. And it is important because the chromosome map of 6388 indicates that is a type 2 globular cluster, and I will explain this later. And this may indicate the presence of a possible metallicity spread. However, based on what we found with our spectra, this is not confirmed, at least not a spread. So a chromosome map is a measure. A chromosome map separates stars of different composition, especially in light elements, because these differences reflect on the absorption line falling in the various filters we are talking about. And those change the magnitudes we measure by very small amounts. By combining filters sensitive to different elements, it is possible to separate, also with photometry and not only with spectroscopy, stars belonging to the first and second generation. And Milone and collaborators, by building those chromosome maps, found that while all globular clusters show the same basic behavior as a chromosome map, so we can separate first and second generation, there are also large differences between them. And here you see the cases for two very famous clusters, 2808 and 1851. And as you can see, their chromosome map looks very different. And in particular, NGC 1851, defined as a type 2 GC, has also this part of the distribution which is not present in the type 1 globular cluster. So type 2 globular clusters are generally high mass, and generally, but not all of them, present metallicity spread, anomalous red giant branch, and variation in Newton capture elements. And indeed, there is a very clear correlation between the position of a star in the chromosome map and its classification in the as a first or second generation stars. So this is a comparison again of 2808 and 1851. The chromosome map were the one obtained by Milone and collaborators, and the stars come from the study we did starting, well, many years ago, and were collected by Marino and collaborators in this paper. So 1851 has all the met all the requests for a type 2 globular cluster. So it is massive, it has an anomalous RGB, it shows a small spread in metallicity and some spread in neutron capture elements correlated with the metallicity. But this is not the case for 6388. And another metallicity spread you may have heard of in recent times is the possible metallicity spread suggested to be present among the first generation stars. And that would explain the very large extension in color of the sequence defined by first generation stars, as opposed to what we find for second generation stars in the chromosome map. And the question is not settled yet. There are many studies addressing the issue, and it is a very important issue because it would mean that first generation stars formed from a gas which was much more, well, less homogeneous than the gas from which the second generation stars formed. But again, in the case of 6388, we did not find any of those metallicity spread. So if we come back to the cluster under study, we studied not only the oxygen and sodium distribution, but all the light elements that are touched by variations. And so we see variations also in magnesium, aluminum, silicon, etc. And all combination of light elements variation can be reproduced thinking of one single class of first-generation polluters. In addition about that, we did not find any indication of strong indication of variation in calcium or scandium, and this helps putting an upper limit to the central temperature of the first generation polluters that we see in this cluster. So in the right-hand plot, you see the variation that we found for various elements. The variation is intended here with respect to first-generation stars, so primordial stars. The precision of the measurements we have permits to study not only the classical elements such as sodium, aluminum, and oxygen, which show very large variation, star-to-star variation, but also smaller star-to-star variation, such as for silicon or magnesium. So all these elements are important to be studied because the presence or absence of an anti-correlation or a correlation with some elements permits to set limits to the central temperatures of the first generation polluters, and based on the nucleosynthetic chains that are involved. So we determined the abundances not only for light elements, but for all elements from the alpha elements to iron peak and neutron capture. Here on the left, you can see the trend of the measures of alpha elements against temperatures, and we see that all those elements show very homogeneous abundances with small spreads, and homogeneous in between stars observed with Uves and Giraffe. And in the right-hand plot, instead, we show the same elements, but in a galactic context. So we show the mean abundances for 6388, here the red dot, and compared to what to the abundances for the other clusters in our flame survey, to other high metallicity clusters measured by the group by Nuyers and collaborators, and by disk and bulge stars. So we see that we have no trends with temperatures, we have small dispersions compatible with errors, and that we see that also that 6388 follows the globular clusters and field star distribution. And if we move to iron peak elements and neutron capture elements, we see again, sorry, that we have small dispersion and no trends with temperature whatsoever. And if we go to neutron capture elements, we see that even if in this case the spreads are larger, 6388 behaves like stars or clusters of the same metallicity. And an important part of this is that concerning the iron peak elements circled here, we do not see any underabundance of them. And I remark this because it is important for the last subject I will touch, that is the possibility that 6388 is an accreted globular cluster and not a genuine bulge cluster. So, like I said at the beginning, indeed, we are learning that many accretion events happened and that globular clusters have been brought in the Milky Way with those accretion events, and while only a fraction of the present-day globular clusters formed in situ. So recently, Minelli and collaborators proposed a method to separate high metallicity stars with Fe over H larger than -1 between those born in situ in the Milky Way and those accreted from satellites. The method uses an underabundance of 3 iron peak elements, scandium, vanadium, and zinc. And sorry, and based on the analysis of archive spectra, Again, the IESO archive is a real treasure chest. They proposed that 6388, the orange dot in this plot, may have been accreted, formed in a dwarf similar to the Large Magellan Cloud, and later accreted to the Milky Way. And that the twin cluster 6441 was accreted too, and this is based on the comparison of the abundances of in-situ globular clusters, like the green one shown here, and the supposedly accreted globular clusters, the black and red dot here. However, they based this on archive spectra of 4 stars in the case of 6388, and with the larger sample we have 185 stars, and for many of them we were able to measure all 3 elements, also for the scandium, for zinc and vanadium, we were able to measure abundances for more than 30 stars. We did not confirm the measurement they got. So while scandium, vanadium, and zinc are indeed useful to detect the underabundant clusters in Sagittarius, formed in Sagittarius, our measurements based on 185 stars for scandium and more than 30 stars for vanadium and zinc, because vanadium and zinc could only be measured on the UV spectra and not on the giraffe spectra, we see that 6388 is similar to the Milky Way disk and bulge filled stars. So we see no evidence of accretion from iron peak elements in our study. And this is also confirmed by what we see if we plot the energy of the clusters against the metallicity of the clusters. And here we have a few separations. So we have main body, main disk, main bulge cluster, main body disk clusters, low energy clusters, and then clusters belonging to accretions event, which are more related to the halo of the Milky Way and not of the bulge. So Sequoia, Gaia-ESO, Enceladus, the Helmi stream, and Sagittarius itself. So the red dot here is 6388, and 6388 sits among the globular clusters formed either in the bulge or maybe in the disk. There may be some ambiguity with the low energy clusters, but then if we look at the age metallicity relation, where there are 2 relations for the accreted clusters and the in-situ clusters, we see that 6388 sits clearly among the clusters formed in situ. So I come to my conclusions, and I come to the end of the presentation. And since I presented the conclusion at the beginning, I wish to add something on the future plans. So personally, we intend now to proceed with the 6388, and we want to target and to add also potassium to our list of elements to study, because potassium is anticorrelates with light elements abundances, but only in a few globular clusters. And this gives an information on the maximum temperatures of the nucleosynthetic chains that produce the proton capture elements. We also wish to extend this same kind of study to NGC 6441, which is considered a twin globular cluster. It is a very metal-rich, old massive clusters residing in the bulge. And also in this case, we will try to combine archive and new observations. So we have submitted a proposal for that, and we hope it will be approved, but we will learn in the next month. And finally, I know that the flames is still a very efficient spectrum for stellar clusters, and it is important in comparison with even with the large surveys that are ongoing or will come in the next future. But in particular, I wish to say one thing about WEAVE and Foremost. WEAVE and Foremost will study some globular clusters, or at least all globular clusters visible from the southern sky. And we will see results in the coming year. But one important feature of those two instruments is that with their very large field of view, very, very large compared to everything we have used today until now to study globular clusters, like, well, for photometry, the space telescope on which the chromosome map have been built, or flames, which have been used to study the central part of the globular cluster. Those two instruments, WEAVE in the north and Foremost in the south, will permit to study the whole cluster, following the cluster from the central part to the tidal radius and also beyond that. And with this, I thank you for your interest and stop my presentation.
Thank you very much, Angela. Indeed, a very precise and careful study was done for this globular cluster, and the results are very important and trustful. So who has questions? Sara Lucatello, please.
Hi, Angela. Thank you for your presentation. I'm curious, can you go back to when you compare your results with the ones in the plot where you showed, the first plot in which you showed you don't have the same abundance ratios as previous studies that have attributed to 6388, the fact that it's been accreted. Just
Sure.
if you can show that plot.
Yeah.
Yeah, that one, exactly. So my curiosity is, did you reanalyze any of the stars that Minelli used? And if so, do you get the same results?
Okay. Those stars, the Minelli stars, were already analyzed by us because the archive spectra they used were obtained in our original program in 2004 or 7. I don't remember exactly, but one of them. So we had already examined that. And we did a check, though, and some of the differences may be explained by the different kind of analysis. The temperatures and gravities are very similar. So there is some difference inserted by the different solar used. But for instance, so there is a difference, but I think the important part is that we are using a much larger sample than they did.
Yeah, of course. I just wanted to know if there was
sure. And for zinc, for instance, this is important because zinc is measured from one single line in the bluest part of the US range. So either you have a very good signal to noise, etc., or you may be in trouble. So we got more data than they did, and with higher signal to noise. So I think this partly explains the difference.
Yeah, thank you.
Well, I think that those three elements are not among those for which most precise abundances could be determined, because, as you told, just one line or several lines can be analyzed, and vanadium is not a simple element.
No, no.
However, for your conclusion, the next plot where you compare in the next two more slides.
That okay. Yeah,
Is it,
yeah, no,
this
it is not only
quite
one line.
convincing.
Yeah, not only one line or so. It is, as I said, it is in the bluest and so less well exposed region of the spectrum. So even determining the continuum is difficult. So
Yes.
So and this is a metal-rich globular cluster, so the continuum is difficult to trace anyway. So that's, yeah, and this helps. Yes, I think this helps. So
Who else would like to ask? Angela? So our galaxy has quite complicated formation history, and still a lot of studies should be made. And interesting that in the bulge, in the very center of our galaxy, we also observe those accreted clusters. So very interesting to investigate.
yeah, and besides foremost in the case of 6388, but it will be difficult for them. There is another instrument also mounted at ISO telescope, well, which will be mounted at ISO telescope, that will be ideal for the bulge cluster, and that is MOONS, because MOONS works in the near infrared and infrared. So it will help study clusters in the bulge, even clusters much more absorbed than 6388, which was, well, an easy task even for optical spectroscopy. But if we really want to do bulge clusters, the absorbed clusters, then we need to move to the infrared. But
Okay.
the resolution is less, maybe you obtain less elements, but it's a compromise between the possibility of observing them or not observing them at all.
So we expect to receive many more results from the foremost survey.
Sure, it will be in a few years' time, because foremost will be mounted in about, well, we'll start in about 2 years from now, but then we need to analyze the data. But I insist that even if we have the large service, there is a lot of work to be done by smaller works, using flames, for instance, or high-resolution spectrograph everywhere, because we need to study details, also details of the clusters. For instance, if we want to see if there really is a spread in metallicity among first-generation stars, we need to do a very well, precise analysis. And so even if we observe 20 stars and not hundreds of stars, and we do it with a lot of care, then it produces an important result. So I advocate the case of small and precise analysis, not only of large service, even if I'm part of Foremost, and we proposed together with Sara Lucatello and Antonella Valenari and many more a survey of stellar clusters with Foremost. But I believe in the combination of small and large projects.
Yes, I always emphasize precision in such studies, and sometimes in smaller projects the precision is better, more attention could be given for the analysis. And I would like to ask, maybe Eugenio would like to add something to the presentation. You are the co-author of this study. No, we do not hear from Eugenio.
I believe he has problems because he's connected from home, and I think he has a bad connection.
Okay, so thank you very much, Angela, and I encourage other scientists to present their results and share experience. So you are welcome to apply for your talks, and see you again.
Thank you, and thank you all.